Okay, so if there are no questions, let's start with today's guest speaker. Again, we are kind of honored to have Nived giving us a talk on reinforcement learning. Nived is at UC Berkeley, and Berkeley is one of the powerhouses in reinforcement learning, has always been for a while. And, as you might have read in LLMs, also there's like a resurgence of reinforcement learning, reinforcement with human feedback, reinforcement learning with in reasoning models, and Nived has been doing some of the latter work more recently. But he will talk to us generally about reinforcement learning, and towards end talk about reinforcement learning in LLMs. So go ahead, Nived.
Yeah. Thanks for the super kind invitation, Inderjeet. Let me just share my screen. Okay, yeah. So, yeah, as Inderjeet said, I'm going to talk about basically an introduction to RL, but I want this to be as sort of a discussion format as possible. So feel free to just unmute yourself or raise your hand in the chat, and either I think one of you, either Inderjeet or Nilesh, you can help me out in case I miss something in the chat. Um, Okay, so yeah, I'm going to talk about RL and toward the end, maybe give you a little bit of a modern take on RL and how people are using it in the context of reasoning models and also, more generally outside of that these days. So yeah, what's the basic thing I'd like to first discuss is what's the distinction between ML versus RL? Why do we have these two different words? And so you can think about machine learning as sort of broadly including RL as a subclass, but just if you wanted to make a distinction, you can think about ML as being sort of like learning patterns in static data sets or from static distributions. And so these are a few examples of models that were trained to do this sort of task, where you're asked to classify or you're asked to generate, data that looks like a certain type. And the theoretical analog for this is like learning from IID data or data that comes from the same type of distribution. But in the real world, data is not always IID and it's not always static. Things are changing, things are moving. Nothing is really stationary, and so it makes sense to study things beyond this framework. And so I'll motivate that in the next few slides. So, anyways, the implementation pipeline of how you would think about this machine learning system is you kind of go out in the world, you collect a data set. So the data set here might be labelings of images, segmentations into cats and dogs and animals in general. And then you train on this data set. So you have a sort of supervised learning framework. You have a bunch of data points and you have labels for them. And when you deploy this in the real world, you might hope that the model kind of generalizes. So over here, you have this like picture of a cat or a dog and a bird mixed together, and you hope that the model is able to identify the two components based on the respective features. And so this is what an ML pipeline would look like. But RL is sort of like a version of this problem where things are not stationary anymore. So you should think about this as learning interspersed with some form of decision making. And so the implementation pipeline you can think about from the perspective of like, let's say a self-driving car is the self-driving car might take an action in the environment, which might mean that it decides to press the gas pedal or it decides to take a turn to the left or to the right. And once it takes this action, it kind of sees how the environment changes, how the world responds to it. So in this case, if it for instance would happen to take this left turn when there was a red signal in front, it learns that maybe there's an accident or something like that. Well, this is not the way we would want these models to learn, but it's a sort of simplification of like how the data collection process looks like. And so you collect this data and then you feed this back into the model, and there's some mechanism for feedback where the model takes the data that you've collected and it learns what it should do and it should not do. And so this is what I call RL, learning from reinforcement. And so the question is, how do we formalize this? How are decision making and learning connected? Because the two of them are confounded in the way I explained it to you. What is the meaning of generalization? There's so many more questions, and I obviously cannot cover all of this today, but hopefully I'll give you a little bit of a taste of how you might think about any of these questions to begin with. So just in terms of the roadmap for today, I'm just going to talk about a theoretical formulation to begin with, which is called the Markov decision process. It's a theoretical framework where you can think about all of these interactive processes, in a sort of unified way. And after that, I'll talk about how do we define optimal behavior, or you need a criteria to determine what is good and what is not good. And so I'm going to talk about that. And part two is a little bit about RL in the wild. What are some practical challenges, including what's called exploration versus exploitation. And part three, I'll conclude with some more modern takes about all of this stuff. So just to go from the ground up, you should think about RL as sort of the formalism as being learning by conditioning, which is what I guess Pavlov did a long time ago. And so the experiment over here is every time Pavlov rang this bell, he gave the dog some sort of food. And so, like over a period of time, the dog started associating the ringing of the bell with food. And so later on in the future, after this dog was sufficiently conditioned, ringing the bell without giving any food made the dog's mouth water. So it would do that in anticipation of food, even though the food may or may not, because these two are uncorrelated events, technically speaking. And so the dog was learning to correlate one event with the other. And so this is sort of like learning to sort of like for the dog to learn this behavior happened as a consequence of reinforcement, which was that it was getting a reward, which was of the form of food. And so, yeah, the positing over here is that the dog's behavior is inherently reward driven, and so you might question that, and we'll talk about that a little bit as well. So, yeah, the traditional ML framework is you train the model to minimize loss, and the equivalence in the RL world is you train the model to maximize reward. And how you specify this reward is entirely up to you, but the goal is really to get the model to maximize this reward. The hypothesis over here is that some form of reward governs what the desirable behavior here should be. And you may or may not agree with this, but a lot of algorithms have built on top of this framework, and they make a lot of sense. And so, again, going back to this autonomous car setup, you should think about maybe some actions being, for instance, not stopping at the stop sign is bad, and so the car gets a reward of -1 for doing this. But then if it were actually to hit a pedestrian, this is much worse, and you get a much stronger negative reward, -1,000. And so the car is going to eventually get incentivized to not do these actions. Okay, so
So
I'll give you
Nived,
this example again. Oh, was there a question?
yeah, I was just going to ask, like, can you go back to the last slide? Here, the analogous for reinforcement learning is maximize reward. Is it just the name that we are changing? Like, we can also say that, okay, you can maximize the negative of loss.
Oh, yeah, no, that's a good question. So I think this distinction is not yet clear from the way I've described it right now. But when I go into the next few slides and define what it means to maximize the reward, how this objective looks like, it'll be more clear to you that they're not the same thing.
Okay.
Okay, so yeah, again, I'm just trying to drive this point home, but slowly work toward what a formalism would look like. So again, from the point of view of a self-driving car, you can think about the cameras of the car as seeing all around, and so there's a sort of state that is captured. So there's a rear camera, there's a like a medium range camera for medium range distance, and so on and so forth. So there's a lot of different sensors around, and even though this is not as rich as the actual three-dimensional world, it's a fairly rich representation of what the car is seeing around it. And this is really what it's using to tell where it's at the world and decide, like what it should do or should not do. At the same time, there's also an action, and these are like two portions of what are usually a much larger set of actions that the car can take. So here it's just like steering the wheel or pressing the brake or the accelerator pedals. And yeah, as the car drives around, it stops at that stop sign, so it gets some sort of reward. And maybe at some point it decides not to stop and it gets a negative reward. And so I'm just like tracking that at the top over there. But over a period of time, this car is just like in real time experiencing these things, and maybe it's like updating its behavior on the basis of that. Okay, so yeah, how you can think about this is again just abstracting that away. There's a state S, and you initialize in some sort of state that's drawn from a distribution, and you pick an action, and then you go to a next state. S prime. And so the next state might not even be deterministic. For instance, there might be a transition, a random next state that you're drawn to. So there are many cases where it's deterministic, game solving and so on. I'll talk about this more. Um, but there's no restriction on how the next state should look like. It can be drawn from a distribution itself. And based on what the next state, which next state was played, or sorry, I should say, based on the current state and the action that was played, you transition to a new state, and you also observe a reward R of S comma A. And so this is like the driving signal that determines what's good and what's not good. And you can think about many different ways of continuing this process. So the simplest thing is called the episodic setting, where you repeat this process H times. And I'll talk about another one called the discounted setting a little bit later. And many of the things I'm going to tell you are going to be in the discounted setting, but you should really think about it as either of these things are sort of exchangeable to some degree. There are some critical differences, but they are sort of exchangeable to some degree. Okay, yeah. So this is what I would call a trajectory. So you start out at a state S1, pick an action, A1, you might get a reward. You might even think about the case where you pick a bunch of actions, and then at the very end of this whole process, you get a single reward. So you should think about R1, R2, everything but the last one are all zero, and then the last reward is the only one that's not zero. Okay. Um, so now I think maybe I'll get a little closer to answering Nilesh's question about how these two things are different. So basically you can also think about, you can also it's worth defining what you're optimizing over. And so the learner is what we should think about ourselves being, is defining a policy. This policy is like defined pi, and it's a distribution over actions to play at every time. So you're at a state, and then your policy determines what distribution over actions you're going to play. And that might be a function of the current state, it might be a function of the entire history, might be a function of anything you like. And then based on that, you're going to get transition to a next state. And in this whole process, you might collect a little bit of reward. And so you're going to repeat this process over and over and over again. And you're going to accumulate and accumulate some sort of like total reward. And maybe that's what you're trying to optimize. Okay, so the policy itself is like a function of the current state as well as the history, and it determines what action distribution we are playing. And the learner's objective is to find a policy which maximizes the value, which is like the total expected reward. So this expectation over here, just to be clear, is over like this random trajectory that's drawn out by playing the policy path. So you start out at a state, you play, you pick an action according to your policy, it throws you into a new state. Pick another action according to your policy, throws you into another new state, and so on. So there's the effect of the policy is not over just one step. It determines the next state that you pick, and thereon the state after that, and so on. So there's like a compounding effect of the policy itself. So this is slightly different from the regular, like from machine learning with IID data, for instance, where you should just think about there being no next state. So you should just think about, you play a state, maybe you're like learning a classifier, you're at a state, and which is maybe the image that you have, and you pick an action. The action is like, what do you classify this image into? Do you classify it as a cat or a dog? And just based on that decision, you get a reward, which is whether you are correct or not. And there's no next state, which you're essentially transitioned into. So the effects of the actions or the decisions that you make don't compound over a period of time. Okay, so let's talk about a theory of
I see.
reinforcement.
So the just to get back to the
Yeah.
point that I was trying to seek some answer. So the only difference is that there is a delayed version of the signal.
No, I think, okay, you can think about it as being you get the signal instantaneously, but the
Hmm.
action that you play not only determines your local reward, it also, you're also going to get thrown into a new state, and you're going to encounter new rewards based on the new state. So for instance, maybe this is a world where like you have a picture of a cat, and if you were to classify it as a cat, okay, maybe this is a bit contrived. Let me think of a better example. So um, essentially, okay, the high level point is just that the decision that you make also influences the next state that you see. So you not only want to pick an action that is like going to give you some local reward. Maybe it means that you're picking an action that locally gave you reward, but the next time it lands you in a state that just does not give you any reward anymore. Maybe it just means that you like crash your car or something like that, you won't get any reward further. And so that's not the optimal behavior in this world. You might want to pick an action that's like slightly incorrect. Maybe it does not get a lot of reward, but it still guarantees you to continue to get good reward. So it's the difference maybe between, let's say, you're at a signal and you want to you see that the light is yellow. Maybe
Mm-hmm.
your reward might be maximized if you like uh, locally, maybe you just want to like accelerate really fast and go past the yellow light and cross the road. But the
Mm-hmm.
reward, the risk of doing a mistake is very high, in that if you crash, then you're never going to collect any reward after that point. Whereas if you were more conservative, you stopped at the signal, you may not get much reward, but then going forward, you at least know that you made the safe decision. So you're going to be able to still operate in this world and collect something.
Yeah, I see. But I was imagining like this expectation is still over. I mean, like I could live in a world where I can iterate over all the possible sequences,
Correct.
and then it looks more similar to something like machine learning.
Yeah, yeah,
Mm.
exactly. So I think
But
you're right.
okay,
Like if you
so I guess
abstract this to like, yeah,
the delayed reward coupled with a very big search space
yeah, I think
is
it's
what
more
is
so
leading
here.
to
It's more so
inference.
just the very big search space,
Right.
in that it's like grows exponentially. That is something you just can't tolerate if you're, uh, you know, okay. Maybe these days I should use those words more carefully, but like, I think it is harder to solve that problem, at least just because
I
of.
see. So just yeah, sorry for digging a bit deeper here.
No
Just
worries.
trying to
Yeah.
think like even in case of images, like the search space is pretty big. Like a cat can look like anything on 256 by 256
Correct.
pixel
Yeah.
space, which is a humongous search space. But there, I'm just trying to think like why that search space is not a problem there. Like,
So I think it's somehow just has to do with generalization, and
mm-hmm,
that the fact that we're able to generalize over pictures of cats itself is very non-trivial and it's amazing. But I
mm-hmm,
think the moment you go to like more complex spaces, you're
mm-hmm,
forced to come up with bigger models, because only bigger models will generalize. And so if you're doing something over like, let's say over video, which is like one example where maybe in the sense of video being here, I'm thinking about like, like images in the real world, and then you're taking actions and you see new images, which is what the camera feed would look like. Over
mm-hmm,
there, you actually are blowing up the size of the problem significantly, because you're getting multiple frames every second and you're having
mm-hmm,
to make decisions on the basis of that. So
mm-hmm.
it's just that, if we could have really, really large models that like worked over uh, like many thousands of frames, or like at least they were consistent over that, maybe we can do this. So in practice, there's a combination of the two. We don't just
Mm.
take decisions on the basis of one single step. Maybe it's like you chunk time also in some ways. But ultimately, like the state space is much smaller than if you just looked at the entire sequence as one long problem and tried to solve
Right.
it.
Okay. Thank you.
Yeah. Okay, so let's get back. I'll talk about a theory of RL and like how do we build up from this state and action space formalism that I talked about earlier. So one thing is, what now that I've told you what the reward is and what the goal is, how do we argue anything about what the optimal policy might look like? And so, yeah, let me just remind you again that the value V of pi in red on the corner is just the total reward that you collect, but in expectation over this random trajectory that is generated by rolling out the policy pi on this environment. So I'm going to use this word rolling out. I hope that is clear. It just means that you start out from the initial state, you play an action according to pi, and then you go to a new state, you get some reward, and you repeat this process h times. Okay. So like I said, the optimal policy is the one which maximizes the expected cumulative reward. And the first theorem, which I'll quickly mention, is that there is an optimal policy which does not depend on the history. It only depends on the state that you currently are at. So you should think about it as being there's a pi star which you eliminate history of t minus one, all the previous states and actions that you've seen, and that is sufficient to find an optimal policy. So already this is saying something which is that non-trivial, which is to solve this sequence level classification problem, you can even call it that. Just the structure of the rewards being only dependent on the states and actions means that you don't need a classifier that depends on the whole history itself. You only need a classifier from like states to action. But how you train this is a separate issue. But it suffices to look at distributions from states to actions rather than something that depends on the whole history itself. Okay. So yeah, you can think about this as like the optimal policy as being Markovian, which means that it only picks actions based on the current state and maybe the current time as well. In practice, they even drop the time component. You just train something that just depends on every state, just because it makes the problem a little bit easier. You don't have to train something for every single step. And so, how do you think about this from a point of view of an example? So let's look at the game of chess. And the point is, when you're at the current board state, to determine what the next best move to play is, you don't really need to know how you got to that point, right? All that matters is that you are in that state, and your optimal action will be determined by that particular configuration itself. And so this is basically the essence of this first theorem, which is just that uh, you know uh, for you to just come up with the optimal policy means that you can also do this in a fairly simple policy class, which just does not depend on the whole history. It only depends on the state that you're at. Are there any questions based on this?
Nived, not based on this, but I know that you gave like the example of a self-driving car, right, earlier.
Mhm.
So, I mean, in this case, you're assuming that reward is like a function of the state, right, and the
Correct.
previous
Yeah.
action. What if there is some, fair amount of noise injected, something about the environment, right? Suppose in a self-driving car,
Mhm.
or somehow somebody else ends up making a mistake or something, and so you could, at two different instances, you could take the same action, but
Mhm.
the reward might be very different.
Yeah, that's
Right?
that's
So
very good. So I think
how would you go around handling that aspect?
so. So I think like yeah, just to rephrase your question, I think it's just that when you have you visit a state and you pick an action, you might get a noisy version of the reward rather than the true reward. So maybe
Yeah,
you pick the right action, but then you get a bad reward signal, and so it hurts you even though it should not. This is usually the case in practice, in
I
that
see.
there's some sort of noise or there's some sort of misspecification. It's one or the other. And just training these models on like sufficient amounts of data, and where maybe like a lot of it is noisy, but then if the signal to noise ratio is like reasonable, and that usually it's possible to identify that the reward is like over many trajectories, maybe on average like you're getting the right signal for what
I
the
see.
good action is, then
Oh,
you
I
should
see.
hope that there's some sort of averaging that will kill the badness of.
I see. I see. But you're saying that you don't actually need to try to model it explicitly, right? That somehow that the reward is not just a function of state and action, but it's function of some other features which are kind of unknown.
Yeah, so
The
I think
function remains constant in some sense.
you can try to model that, but at some point there's always going to be misspecification with the
Hmm.
true
Hmm.
reward, which is like usually more complex than that. So in
Okay.
practice, you just model all of the misspecification as just some form of noise, and
Okay.
in practice, you just see that it's like somehow these algorithms are robust to whatever that form of noise looks like. But in
I see.
theory, if you actually try to formalize the noise in some which way, like maybe you have different kinds of noise models. Usually they study the case where like there's IID noise, or like the noise is just like some perturbation on top of the signal that has zero meaning.
Yeah,
The
I see.
algorithms that are proposed are kind of robust to that. They take longer to learn compared to the setting where you have just the true reward signal itself, but they're still like consistent in some which way. Like if you let the number of interactions go to infinity.
I see. Okay.
Feels
Also
like
here itself, like it 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 doesn't it depend on like how I'm defining a state. For example, in the chess case, it could be that I don't have the full resolution, like
yeah,
I
like
just
a
have
view of the board or something.
yeah, maybe like I just have like on a 2x2 patch, how many pieces are there? Or
Correct.
like
Yeah.
so the state could itself be noisy, right? Like the state I'm observing. So in
So
that
that's also a
case,
good question. Yeah, I think there's multiple ways of modeling this as well. And like this, what you said is very true in the self-driving case as well, right? Because the
right,
real world is the actual state, but the model sees it through projections which are like
right.
camera feed or something. So Usually, like there's again two ways of modeling it. Either you just think of all of that as just like noise in like noise in the reward itself. But there's
Mm-hmm.
also this framework called the partially observed Markov decision process, which says
Mm-hmm.
that there's actually a true underlying state that
Mm-hmm.
you don't see, but you always see like some projection of that. Maybe you can think about the projection as being like the image. In the case of what you said, the projection is just like the 4 by 4 area
Yeah,
of the bigger
for check.
area.
Yeah.
Right. Yeah.
So in
And
that case, like, is the optimal policy going to depend on the history as well? Because like I can imagine with the history, I can get a closer view of the true state.
that is true. Yeah. So over there, this theorem is no longer true.
Okay.
Yeah. This you can define it as a function in the same way as a function of independent of the history, but as a function of the state itself. But that you don't see the state means that you
Right.
can't define that policy itself. Like give it, you only see the observations, which are like what are these projections, right? So you don't you have some sort of posterior distribution on what the actual underlying state itself looks like, and it
Okay.
looks more complicated because of that. Yeah.
I see. Okay. Thank
Excuse
you.
me, a question here.
Yeah.
So for example, in games like chess, you
Mhm.
have the liberty to, play it thousands of times and, you know,
Right.
get checkmate and all that, and then, accumulate all those rewards and penalties and find the best path. But how is being doing in like domain like self-driving car? You cannot afford to, go to many accidents or, hitting pedestrians and stuff like that to get that reward. How it's being handled?
So that's also a really solid question. I think my answer to that is it depends a lot from domain to domain because this data issue is there across many different domains. In self-driving, the thing that people do most is one of two things. You either train your model first in a simulator, so it's not going to be an accurate representation of the real world, but it's going to get you some amount of distance over there. And the other thing is, for instance, Waymo and like Cruise and all of the earlier, at least earlier on, I think now they have already started deploying. But earlier on, when they were being trained, they would get customers or like sorry employees at these companies to sit and drive the self-driving cars to get actual sort of demonstrations of how driving would look in the real world. And so all of this is still subject to that you can't collect too much data. There's always going to be a bottleneck, but right now we're in a regime where like we have enough, after spending like millions of dollars, maybe billions of dollars, you have enough data that you can train these models on the combination of like offline data that's collected as well as simulated data as well as some limited amounts of like the model being deployed and like in a safe way and trying to like explore in the environment and learn the right set of decisions to take.
Thank you so much.
Okay. Okay. So this is the first result, which is some sort of like nice characterization of something, some property of the optimal policy itself. And I'll as I go forward, I think I'll try to motivate these things a little bit better. Why do we even need these theorems? Okay. So yeah, I'll also just quickly mention this discounted setting that I alluded to earlier, where we don't think about this problem as stopping at a horizon of age. You just think about this as like an infinitely long problem, but the rewards that you consider are kind of like decaying exponentially. So even if you made a big mistake very far into the future, because the planning problem is harder as you increase the horizon. But here it's saying that like the effects of your poor decisions may be much less if you make those poor decisions far into the future. So effectively, like there's like a discount factor, and it makes like stating some of these results nicer. But you should think about the effective horizon as 1/1 minus gamma. This is like the point till which the number of steps which kind of effectively matter. In that, if you look at time steps which are much bigger than this number 1/1 minus gamma, then the effect of the rewards are kind of insignificant after that point. And this number I came up with just because just when I assume that the rewards are they lie in like -1 comma 1 in this range. But like if the range of the rewards is different, the effective horizon is going to look different. But the point is that there is some effective horizon where you can kind of think about the truncation of this problem to these number of steps as being equivalent to the problem where you don't have any discount factor and you only roll it out for 8 steps. Yeah. So yeah, let me now introduce two terms. One of them is called a Q function, and the other is called a value function. And these are things that you'll see a lot, in RL. So the moment you see these terms, hopefully you'll know what they mean when after I'm done explaining them to you. So yeah, these terms are kind of going to be useful in characterizing what the optimal policy will look like. And the Q function, you should think about this as like, so okay, the order is wrong, but you should think about this as saying, if I'm at the state S and I play the action A thereafter, how much reward would I collect, cumulative reward would I collect if I continued playing after that point? So this is a function of the state S and the action A. And it's also a function of the policy that you're rolling out, pi. And it's saying that once you're at the state A and you pick this action A, how much reward is your policy going to be able to collect? So it's kind of like trying to qualify under your policy pi, how good is this action A at this playing this action A at the state S? So formally, you can define it using this equation that I have over here. So Q pi of S comma A. So this summation over here is just the the discounted sum of rewards, all the way to infinity. But I'm sort of starting this process, starting at the state S and playing this action A. And I want you to think the future actions that are played are being played according to pi. So this is a function of the policy that's being played itself. So again, going back to our chess example, let's try to see what does this mean. So let's say that you're in this position to begin with. So this, if you look at this for a few seconds, you'll see that this is like very close to what's called the scholar's mate position, where the white queen is like very, very much on target to like checkmating the black king. So you just move your queen from h5 to f7. You take that pawn, and it becomes a checkmate. And so you should think about this as like, the game ends over here, so there's no real policy to play after that point. But whatever that policy pi was, playing this red move results in a checkmate. So it results in, so winning the game. So I think about that as like Q pi of S comma A is equal to 1. So this is kind of the trivial case where you define the Q function where you don't have a policy that rolls out after that point. So the effects of your policy don't show up. But a slightly more expressive case is where, let's say your queen was not moved out all the way. So queen, which was on h5, is back on d1 right now. And so you might move to the same square that it were there earlier on. And so this is, let's say, the action A that I want to compute the Q function of. Yeah. So the sort of the board state is the same, but the action A that I'm considering is one move earlier, which is the orange action. Once you've played the orange action, like, I need to specify what the policy itself looks like, my policy pi, right? So the simple thing I've looked at over here is with probability half, the policy actually picks the right move, which leads to the checkmate, and it wins with that probability. And with the remaining probability half, it just, it's not very good. So it might miss this easy chance and take the pawn. And, eventually it plays this game and it leads to a draw. So it does not lead to a win. And so if you compute now under this policy pi, what the value of this orange move itself was given this board state, it is actually not 1 anymore. It's just a half, because the policy only, so it's a half times 1, the half times the probability of winning. Sorry, the reward for winning, and a probability of drawing, which is again a half times the reward for a draw, which is 0. And if you lose, you get a -1, but that does not show up over here right now. So yeah, like, I just try to give you this example to make it clear that the value function depends on the policy that you're rolling out thereafter. It's a function of that. So if you have a poor policy, you'll see the values are typically smaller. I mean, and it won't collect as much reward. Whereas if you have a good policy, you should expect that it collects more reward. Okay. Oh, by the way, yeah, let me, before I say that, are there any questions from this explanation that I've given you? Okay, let me move on to the next thing, then value functions. So again, these are sort of a little bit simpler than Q functions, but they're also worth discussing. So the value function is the expected discounted reward if you start from the state S and just rolled out that policy pi after. So the Q function was if I'm at the state S and I pick the action A, how much reward would I collect for playing the policy pi? The value function says I'm just at the state S and I'm just going to let your policy pi take over from that point on. And what's the total amount of reward that it's going to collect? So it's just the expected Q function where the action is drawn from your current policy pi, because the Q function tells you if you played the action A, then how much would you collect under pi thereon, which is exactly what the value function is also trying to keep track of after the first step. Okay. So just to be clear, this is only a function of the state. It just assumes that you're playing the policy pi from this very state onward. Now I'm going to talk about what's called the Bellman equation, which is kind of like one of the cornerstones of reinforcement learning. And it's recurrence equations for Q functions. And if you're sort of familiar with this, maybe this will be old to you, but it's the high level idea is just that if you want to determine how much reward you're going to collect at the current state by playing an action A, you can play this action at the current state, move to the next state, what according to this random transition matrix that will take you to a new state, and then simply collect, just add up the total value that you'd get from from at that point onward, which is essentially captured by the value function, and you can also write that as an expectation under the Q function. So let me write this down clearly so that you see what I'm talking about. So basically, it looks a little complicated, but let's try to break this down very clearly so that there's no ambiguity. So the Q function, I'm again operating under a policy pi, and I want to compute the total, the Q function at the state S for picking an action A. So when I pick this action A locally at this time step, I'm going to get some reward R of S comma A. And then there's a discount factor, so it affects every future reward that I'm getting. So this shows up over here. And then the first expectation is over the next state that you get thrown into, which is S prime. That's a function of the current state of the action. And the action A prime that you get and you pick after that is a function of your policy, and Q pi of S prime comma A prime just determines how much value you're going to collect at that state S prime for picking that action A prime under this policy pi. So it's kind of just a very simple recurrence equation. And so, again, just going back to chess, which I like to give as an example, is you're at the state S and you're trying to compute the Q value under your policy pi for this action. And so, in this case, there's no reward because you only get the reward at the very end where you either win the game or you draw the game or you lose. And so there's no reward at the step. But then with probability half, you pick, this action that leads to the checkmate. So there's some Q value for that, and we know that that's equal to 1. And with probability half, you take the pawn, and that eventually leads to a draw. So that has some Q value, but we know that's equal to 0. And so that equation just exactly calculates the number of 0.5 that I told you earlier. Okay, so that's the first step. Now let's try to actually use this sort of Bellman equation to characterize what the optimal policy will look like. And so this is called like Bellman's optimality equation. And so what this says is it's a very simple form which tells you exactly what the optimal policy will look like. And it's again a function of this recurrence equation. So it says, let's say somehow you solved and you told me what the optimal Q function is. So this is the Q function of the optimal policy, pi star, at every state comma A. So it's kind of like a cyclical definition. So maybe you might have a problem with this, but it's still well defined once you have defined Q of pi star, which is just some function. So what this says is if you've defined the optimal Q function, Q pi star of S comma A, there is an optimal policy, which is you just play greedily at this step. So what this means is that at this step, you look at all the values across all the actions, and you simply pick the action that had the largest possible value. And so even if there's a tie, you might pick any one of them arbitrarily. It does not matter which one you commit to. So basically what this says is the optimal policy, sorry, I should have called this optimal, not expert. The optimal policy can be deterministic. It's not necessarily is deterministic. There are also stochastic policies sometimes. And this one picks the action which has the largest Q value, Q value under its own rollout distribution pi star. Okay, so the sort of high level idea is, again, maybe I'll skip this plot and I'll just go to the next one, which explains this through chess. So yeah, again, let's just say that Q pi star, you want to compute it for this particular state at this action. And you have two choices at the next state, which is you either, you sort of take this pawn and you win, or you take this other pawn and then even under your own optimal playing strategy, maybe the game ends in a draw because let's say black knows how to draw. Then what this says is at the first stage, the right move to have done would have always been to take the pawn. It's like the optimal policy would always pick this action, and that's witnessed by the fact that the Q value at the first for the first state for the first action A1 prime is higher than that for the second action A2 prime. Okay, so yeah, I've been talking about a lot of theory so far. So let me sort of like wrap this up with this one last result, which is sort of an optimality, like the Bellman equation when you sort of plug in this optimal policy, and it just gives you a recurrence relation for Q pi star. And so what this is saying is for the optimal policy alone, you have this recurrence form for it. And all this uses is the fact that the optimal policy just picks the action with the largest Q value itself. So this max over A, you should think about this as just an expectation over the action that the optimal policy played. And that's the same sort of form that you had in the Bellman equation that showed up earlier itself. So yeah, the nice thing is, okay, before I go any further, let me just stop here and ask if there's any questions. This will be the last sort of big theoretical thing that I'll show you. But these are the basics, so it's worth knowing all of these things. Okay, so yeah, the nice thing is there is a very simple algorithm which is called value iteration, and it can actually solve this recurrence relation approximately. So given the transition P, given the reward function R, you can plug you can use this algorithm called value iteration to solve it and compute what this optimal policy should look like. So that's nice. But this assumes that the MDP transition is known. It assumes that the reward function is also known, and these may not always be the case in practice. And more importantly, it also really only works when the number of states and actions are kind of finite and small. So when you actually look at these practical problems, for instance, like self-driving, or later what I'll talk about is in the case of LLMs, the states and the actions, the number of these may blow up, and so you really can't computationally, you just cannot implement an algorithm like this. At least naively you cannot. So you need to do some sort of tricks to get it to work. So that brings me to the second part of this, reinforcement learning in the wild. So before I move on, because this will be the last I'll be talking about some of the theoretical stuff I brought up. If there's any questions about that, including like any sort of intuitions for how to understand any of these results, just feel free to ask me. Okay. So there are no questions. Let me move on to the next part. So what are some practical challenges in deploying these RL algorithms? So there's several challenges. First of all, yeah, like I said, the rewards and transitions may not explicitly be known. They need to be learned. And at the very least, maybe the transitions are sometimes deterministic, so you don't have to learn them. You may know them already. For instance, if you have a simulator for your game, then you know exactly what playing an action is going to do to the next step. Maybe you even have an explicit small network that gives you this. And when I say network, not a neural network, just some sort of algorithm that gives you this. But the reward function is often usually harder to learn in that it can be misspecified, it can be noisy. It could also be the case that it's just not well defined. Like there may be problems where you might think that the reward should be one. For instance, cases where there's like ambiguity, right? Like maybe there's questions about morality or something about ethics. The reward function just may not be well specified at all. So all of these challenges will show up as you deploy these algorithms in more and more complex settings. The second issue, which is more algorithmic, is the state and action spaces can be massive. And like I said, this is the case in self-driving cars, this is the case in LLMs as well. And so how do we generalize from a small number of interactions? This is not super clear at all. And yeah, rewards are often very noisy, or they're not aligned with human objectives. So how can we robustify our algorithms towards this? And so again, the point here is that we don't have a good way of specifying what rewards might like. So how do we, have algorithms that understand that, and they might be robust to that? So a core to some of these challenges are what are called the exploration versus exploitation dilemma. So yeah, like this is a kind of comic that explains to you what's going on over here. So uh, the first person is kind of like they dug very shallow and they found this gem. The second one is also digging in their pit, but they don't see, they haven't gotten any gems so far. So the first person goes away. The second person realizes, okay, the first pit is the one that probably has all the gems in it. So he starts looking over there. But all along, there was just like, they were just like one step away from finding this big gem that was in the second pit. So the point is, when do you decide that you want to explore? Explore here being you want to commit to this second pit, which may not have given you any reward so far, versus you want to exploit, which is you saw that the other person got the gem, they got the reward, so maybe you want to also go and follow in their footsteps. And this sort of challenge occurs a lot in practice because exploitation often also means safety. It means that maybe you're staying in the realm of things that and so it means being safe. And exploration also sometimes could mean that you're doing things that are unsafe. Maybe this means that your car needs to, naively, it needs to like, run past like 10 red signals before it learns that crossing red signals is a bad thing. And it probably has to do this in many diverse environments to learn that this is a bad thing. So this is the the rephrasing of the same kind of challenge, which is how do you determine how safe you want to deploy your algorithms versus how well they can learn given this new, given that they don't have to be that safe, maybe they can try things that they would not have done otherwise. So yeah, we do want to explore the state space to like discover new states which are good, but at the same time we want to pick actions which are greedy with respect to our q function estimate. So this is like a mathematical formulation for what exploitation itself means. We have some q functions, and the q functions just tell you like what you think different actions are at the current states are worth, how much they're going to how much reward they're going to give you if you played those. And maybe the right thing for you to do is just play greedily with respect to that. But this is with respect to your noisy queue function. You've learned this from data, you've learned this from like limited amounts of interaction, so it's not going to be very good. Uh, and so the simplest idea, which is like one way to do exploration, is exploit with probability 1 minus epsilon, and you explore a uniformly random action with probability epsilon. So this is kind of like a very simple approach. And like this is actually a lot of, there's a very complicated exploration algorithms you can come up with in practice. But in a lot of especially robotics like environments, this is an algorithm that works really well. So I just have this like simulated cart pole task. And so the goal is just to keep the pole in the vertical position by moving the platform either to the left or the right. So there's gravity which is trying to bring the pole down. And so I'm going to show you a video which is just like implementing this deep Q network and epsilon greedy exploration. So the this is like at test time. The model was like, or this algorithm was, the RL agent was trained at training time using this greedy exploration. So it made many mistakes while training. It fell down many times, but then it kind of learned diversely how to solve this problem after many rounds of interaction. So yeah, it does a fairly good job. Maybe the question over here is not even whether it can solve this problem or not, which because it's fairly simple, but how quickly it can solve this problem. And epsilon greedy exploration does a fairly good job at that. So I'm not going to go into too much more detail about exploration versus exploitation. This is a whole field in of itself, and there's a lot of work that has come out, both theoretical as well as applied. But this is just to give you a taste of what you would want to do while training these methods. Are there any questions?
I guess, typically, I know that you said like the number of states and so on is like a computational challenge, but like in applications that you know of, typically, what is the largest number of states that methods can handle reinforcement
So for
learning?
something like this, it's probably very small, because just because you can technically it's a continuous environment, it's a continuous state space, but you can discretize it and you can do fairly well. But if you think about a game like chess or Go or something like that, it's already there's a blow up in the number of states. Like, the number of possible positions is essentially what you need to deal with. But maybe you won't encounter all of those positions in practice, but it's still like it still blows up. It's still exponential in like the size of the chessboard, for instance. But then if you go to actually like LLMs, where also reinforcement learning is being used, I'll talk about that in a little bit. There you again have the same kind of blow up, because the number it may even be that the number of actions at every step is discrete, but the length of the solutions that you generate is just really, really long. So again, the total number of sequences, the number of answers that you could have possibly generated are really large. So you need something to control these state spaces, essentially. Like, either you have some algorithm that's very clever with how it explores in the state space, and that is the case with LLMs, for instance. Or maybe you have like a some like side information. Maybe you have someone has solved, given you demonstrations of like solving how this problem could be solved, and maybe you use that to bootstrap your learning algorithm itself. As such, like learning in the wild just without any feedback is like usually intractable.
So, by the way, are there methods who also do some form of latent state projection, which makes the state space manageable, and or do RL on top of that?
Yeah, so there's actually a lot of work like this, and I think maybe, I mean, like I guess I could not enumerate the number of such papers because there's too many of them. But one that comes to mind is that does this really well, I think, is there's this paper called Go Explore, where they try to solve Atari games. And for Atari games, like usually the challenge is, they're kind of like the easy ones are easy, the hard ones are very hard, and so best algorithms won't do very well on the hard ones. But this paper showed some like very nice techniques based on this, like compressing the size of the latent space, and also some like very clever exploration techniques that they come up with that like it beats the state of the art by like an order of magnitude in terms of the score itself on Atari games.
And I guess you're probably going to talk about a little bit about LLMs and
Yeah,
trying
yeah,
to
yeah.
do maybe reasoning, but there's also this work that is ongoing, right? About trying to reason in
Latent
latent
space.
space. Is that somewhat related or?
So I don't think they do reinforcement learning. Or maybe actually they do reinforcement learning. So I think it is probably closely connected. I think what they try to do is project the whole reasoning trace into some sort of like smaller dimensional latent space, and then try to do RL. Again, you're trying to still solve the end problem, which is like trying to solve the math problem, which means you're trying to collect some reward at the very end, but it's done by doing the optimization within this like smaller latent space itself. So it's like less clear to me that it's directly of the form of projecting the state down itself. It's like maybe more abstract notion, because you can project a sequence of states and actions into this latent space. It's kind of like an embedding space basically. But yeah, it's like very closely related. Um, but I will say that like the challenge of um, having really large state spaces, even without these abstractions in LLMs, to some degree has been like we know algorithms that like do well even without the projection down into the latent space. So I think it's nice that we have those things, and there's more to build on top of that as well. Okay. Um, Yeah. So again, I'm just going to go over a very brief survey of like some of these like existing methods. These are not state of the art, like maybe I'll put it that way. Some of them maybe are toward the end, but yeah, there's like a lot of work in RL about like how to train these various components. Maybe you train your policy, train your value function, and so on. So anyways, the distinction is usually into three: value-based methods and value and policy-based methods. And there's also soft actor critic or actor critic-based methods, which maybe like lie in between these two things a little bit. So value-based methods basically try to train a model, which is usually a neural network to learn the Q function.
Sorry, Nived, just to make sure you're not showing any slides right now, right?
Oh, wait.
He is. I can see the slides. Are you not able to?
Somehow the slides for me went away, but
Oh.
I don't know if the others can speak up if they see the slides or.
Yes, we can see the slide.
Should
Okay.
I
Okay,
stop
yeah.
sharing
Somehow.
it, reshare
Oh,
it
no,
maybe?
it's fine. I think I ended up moving to a different screen or so. Sorry.
Oh,
Yeah.
okay.
But just a quick reminder that we have about 16, 17 minutes left. Huh?
Yeah,
So,
okay. I have just a few slides, so it should be okay. Yeah. So yeah, the value-based methods basically train an RL agent, which is like usually a neural network to learn this like optimal Q function. And how you train this optimal Q function is if you go back and you rewatch this video, you'll see this like optimal Bellman optimality equation, and you try to solve this recurrence equation. This is exactly what these algorithms are trying to do. And so this is what I call Bellman backups, and this is the term that's used. We try to use this Bellman operator to update the value function and try to come up with these like optimal value functions, basically. Once you've come up with them, then you can try to just play like once you have the value, given a state and given an action, how much you're going to collect thereon. You exactly know like exactly how to optimize this particular object. And this is usually done with a technique called experience replay to smoothen training. So you kind of don't purely do this. You use data that you've already collected, may not even be from the policy that you're trying to optimize currently, but you can use that to kind of smoothen the whole training curve out. And so yeah, there's like the famous deep Q network and double DQN. These are like some of the very classic algorithms that are value based. There's also policy-based methods where the agent tries to train a model or a neural network to approximate the policy directly rather than implicitly going through this Q function. And you use the policy gradient theorem to update the policy. This is usually the case, and I think this is also the core behind what are called actor critic methods. And these are usually the ones that are implemented in like very large action state and action spaces, and when there's continuous state and action spaces, just because they go through some like nice tools that we've developed in optimization to solve these very hard problems. And so there's a lot of different algorithms that fall in this bucket. And notably, like reinforce is one of the first ones that a lot of these approaches build on top of. Their variants on these to make the training smoother and to make the training less spiky, because reinforce. I'll cover this in like a little bit of shallow depth. Let me say it that way. Just because it'll end up having very high variance in the updates themselves. And so these are like newer variants that are proposed, and there's some more work that I'll talk about toward the end that sort of like builds on top of this line of work. And so yeah, some of these approaches, and I'll say this as reinforce and PPO have been used quite extensively in training LLM reasoning models. And also there's more modern versions of these that people use these days to actually train the models themselves. So yeah, this gets to the last section of the talk, which is a shallow dive into LLM reasoning. So I'm going to focus on math reasoning as the main sort of domain of application, but you can try to think about this in other domains as well. Maybe some of the specifications will change, but fundamentally, like reasoning in across many different domains has some similar qualities across different domains. So the initial state, of this like Markov decision process, this is like very large Markov decision process where the initial state is the prompt. It's a very complex looking initial state. It has many tokens, but this is what how it's framed usually. And the actions that you pick are kind of like the tokens that are generated by the model itself. And so you can accumulate all of these actions that were played previously into like a giant state, T1, T2, all the way to TK. and the reward is basically only at the very end, and you can kind of get this is equal to 1 if the answer is correct, and if it's 0 if it's not correct. So there's lots of questions about how do you even extract the answer out of like a model that generates this large response, and also what's the right abstraction for thinking about states and actions, because there is differing evidence about how to think about this. Some works think about a whole math step, maybe the first equation we can write, and then followed by this first equation, this whole first step as like one single action. And other ones, like the way I've explained it to you, think about singular tokens as being the actions themselves. And so this is like, though, if you had to like think about this from an RL point of view, this is a sparse reward Markov decision process. And sparse reward just means you get the reward at the very end. Even though you kind of do get rewards in the middle, they're all zero. So they have no information about the correctness or incorrectness of your current solution. And it also has deterministic dynamics, because exactly when you pick an action, exactly what the next state is going to be like. So it's kind of like chess is an example of also another environment which is sparse reward and has deterministic dynamics. So that's one reason why you might think some algorithms that work well for chess, like RL, might work in this domain as well. And so now I'm going to spend maybe like 10 minutes talking about policy optimization methods to reinforce PPO and more recently GRPO. But I won't go into a deep dive on this. So if anyone has any questions, feel free to just reach out to me after this, and I'm happy to talk more about this. So let's build this up from the ground up. So first of all, I'm going to talk about reinforce, which is based on this policy gradient theorem. So the goal is we want to maximize V pi, and I'm going to represent that as V pi theta, just to make it clear that there's like some underlying network that's being optimized, and let's say theta are the weights of this network. And so you're trying to like maybe optimize like here I'm phrasing it in this way because there's only a reward at the last step. So the expectation of under this policy pi theta of the reward at the very end. And so you could just ask, why don't we just run like gradient descent or something? And I think this is related to Nilesh's question in some which way, which is even though maybe this objective does not look the same as how you're just doing, like, let's say just like writing down the log loss or something like that, a cross entropy loss for a classification problem, you can still use the same optimization tools to try to solve this. So for instance, you use SGD or RMSprop, Adam, any of these algorithms, and the policy gradient theorem is exactly what tells you how to do this. This like compute the gradients of this objective and like update the parameter theta. So let's like write this theorem down. So this looks a little bit complicated, but let me try to motivate this as best as possible. So let's just say that a learner's policy is parameterized as pi theta. Then the policy gradient theorem exactly tells you, it's like a closed form, or maybe not a closed form. It's an expression for exactly what the gradient of the value of the policy looks like. And so basically, this is an expectation of some quantity z under the policy that you've. So this z is a function of the whole trajectory that was generated so far. And this expectation is under the policy pi theta that generated this trajectory. Now, z has an explicit form. And, I think like you can derive this and come up with this expression, but motivating why this is the right objective is not going to be easy for me to do right now. So I'm just going to like keep this as as what it is. It's just like basically computing the gradient of the logarithm and multiplying that by the q function itself. The intuition is that if you compute the gradient of the log, the gradient of the log is like of a function is like the derivative of the function divided by the function itself. And so when you compute the expectation of z under pi theta, there's some cancellation that happens, and you end up just getting the gradient of the function like the pi theta itself, which is what you would expect from the get-go. So okay, like without diving into what this quantity z itself is, the main point of this theorem is you can write down the sort of like the gradient or the so let me remind you why what the hardness of this problem is. The hardness of this problem is as you're at a state and you pick an action, you transition to a new state where you pick a new action, and so the effect of your policy compounds over many steps. It's kind of like a nonlinear effect that you have. And so because of this nonlinear effect, computing gradients becomes very difficult because small changes in the policy right now could like potentially lead to large changes downstream. Um, and so the policy gradient theorem just tells you like an explicit way of how to capture exactly what this scaling looks like. And what this says is you roll out a policy according roll out a trajectory according to your policy, and you compute the expectation of the z quantity, whatever this thing is. Okay.
Just a quick
So
clarification. The
yeah.
skew pi theta is you get from the Bellman equation or something.
So yeah, okay. That's a. I think I'll get to that very quickly. So this
Okay.
q function is the q function under the policy pi theta,
Yes,
and pi theta is the policy that you're optimizing currently. So
right,
someone needs to tell you what this q function is,
right.
and usually you don't have this q function, or you don't have access to it. You need to learn it as well. So there's one step that is missing over here, which tells you how to actually update or learn or train q theta itself. And that differs a lot from algorithm to algorithm. There's many different ways of doing it. And I'll talk about very briefly, just mention one at the end of how to do it. But yeah, that step is not specified by the policy gradient theorem. It just tells you if you had the Q function, then you do your update in this particular way.
But given a pi theta, can't I just, I mean, in theory, can't I just write out the q pi
In
theta?
theory, you could. You can write this down explicitly. The issue is in practice, you cannot because it means
Sounds,
that you have to roll out your policy and like
yeah,
compute
yeah,
from this state and for picking this action, what's the future reward you can get. You
yeah.
can try to like average a bunch of times, but doing this for every state and every action is going to be difficult. And that's
Got
this result expects you to be able to do that at
it.
least. Yeah. So okay. So to motivate this, let me just explain the reinforce algorithm to you, which I think does a fairly okay job at motivating it. So the algorithm itself says you just generate a whole trajectory by rolling out pi theta, and then you just update the parameter theta by computing by doing gradient descent. So I think I should be a little careful here. This should be plus eta times z hat because you're trying to maximize the objective, which is the value itself. But yeah, basically you're running a gradient update, a simple gradient update to update the parameter. And z hat is basically what z would be if you just computed the value of z on that one single trajectory that you sampled from the current policy pi theta. So you iteratively run this thing. You have a pi theta, you generate a few trajectories, you compute the z hat. Maybe it's averaged over all of those trajectories, which is what happens when the many batch size is bigger than one, and then you just update your parameter theta according to this. So the only difference between this and just a regular gradient descent is you need to write down this explicit form, just because the loss function depends on the non-linearly on the object that you're trying to optimize itself. That's the only real thing going on over here. Okay. um, so yeah, just two FAQs basically. So first one is what Nilesh asked. So to compute this z hat or to even run this policy gradient theorem, we need an estimate of the Q function. And how do you do this? There's like a lot of different approaches that do it differently. So famously, the PPO algorithm, which is like used a lot these days, it uses this approach called generalized advantage estimation. And GRPO uses something much simpler, which is called leave one out estimate. And again, I'm not going to talk about this now, but I'm happy to discuss this after if anyone is curious. The second question is every gradient update that you do, it relies on generating a new trajectory from the current policy. So you should imagine that you have pi theta, you roll out a few trajectories, you do one single update, and the trajectories that you generated before are kind of not used anymore. They're thrown away. So for the next parameter, you redo this process again. And so, this is kind of wasteful in some which way if you think about it, because your policy is not really moving too much from one update to the next update. And so you might reuse data from the past using importance weights. And this is again, just one of the tricks that's used in PPO and GRPO to get them to work. Okay, so I'll just end this section just by saying GRPO is like one of the main driving RL algorithms behind DeepSeek. So it's worth, if you've not heard of this, it's worth knowing what this algorithm is doing. And this was not also the first sort of work showing the utility of this algorithm. There was earlier work from DeepSeek from over a year before, which trains much smaller models that also achieve like state-of-the-art performance, by using this RL algorithm. So all this to say just that there is some utility in looking deeper into what these algorithms are doing. Okay, so let me conclude very quickly. So there's
So,
been
so just,
oh, yeah.
Nived, if you just go back. So is there, I mean, at least from, what you said above, right? It seems to say that, oh, you could use PPO or you could use GRPO. So, but then below you say that, GRPO is the one that kind
Yeah.
of gives the really big advantages. So, like, how do I reconcile? I mean, is GRPO critical, or could one have used PPO there also, or reinforce, or some other variant, and it's something else that they did that made everything work?
Okay, yeah, this is a really good question. I think so. I have two answers to this. One of this is uh, PPO itself is a pretty unstable algorithm to begin with, even though it is the stabilized version of reinforce, and it's unstable just because um, like the model is you're like you're both training a policy, which is using this like the policy gradient theorem. You're also learning this q pi, which is like a value function, right? So like or the q function itself under the current policy. So I haven't again discussed how that learning is happening, but there's two objects being learned simultaneously, and one of them is relying on the estimates of the other to like update itself. And so just because of this, if you have a q function that's not optimized very well, you'll encounter what's called reward hacking. So like the policy that's trying to optimize, it's like it sees a queue function which you've learned, but then maybe your queue function is it's very inaccurate on some regions of the state space, some kinds of solutions. Maybe these are like spurious solutions. For some reason, the queue function was not learned well, so it thinks that should have very high state, like very high value. Then when you're trying to optimize the policy itself, it might go towards that region spuriously, which is not good. So you have this like issue that there's two things being optimized, and if one of them it's compounding errors. If one of them slightly off, that will make the other one slightly off, which will make the first one slightly off again, and so on. That like makes this whole thing unstable. So PPO is unstable. Reinforce is also unstable for the very same reason, just because it relies on learning a Q function. GRPO solves that problem in a very direct way, which says, uh, I don't know how to compute this Q function. It's very complicated, and it's hard to optimize that. So I'm just going to use an empirical estimate of the Q function. So I'm just going to look at the current state and the current action that I'm at, and I want to compute the Q function over here. I'm just going to roll out a bunch of trajectories. So this is the silliest thing you can do, but it somehow it like it's in a regime where the amount of compute you need to be able to run GRPO and the stability of the algorithm both are like very good, and so that just makes it a better candidate right now than PPO.
Okay,
So
thanks.
yeah, I'll also just say that like I've tried running some experiments on my own between these two, and I think even though that the original like the DeepSeek paper does not make this distinction very clear, PPO is a bit more unstable than GRPO training wise. So you need to do some tricks to get it to work better, but simplicity wise, like it seems like a nicer algorithm to just use GRPO.
Thank you.
Okay, so let me conclude. Yeah, so I've tried to talk a little bit about how LLMs have been used a lot, and the last thing I spoke about is RL is being used a lot, and specifically in the domain of LLMs, where we see them being used in reasoning models, and also they were used a lot. PPO is used a lot, uh, in RLHF, where you kind of use it to align the model to a reward function that's learned. And game solving, this is another domain that I think we've seen a lot of work in the last 10 years, where the current agents are now like much, much better in terms of ELO score. They're much better than the best humans at a lot of these different games, chess, Go, shogi, poker, and so on. Autonomous driving has also been greatly sort of, influenced by other. We've seen a lot of these companies have like deployed successfully in many of the major cities, and including Austin, for instance. And robotics, there are also many interesting, challenging problems, especially in like grasping and manipulation. But we have seen a lot of recent progress in the last two years or so. on robotics that's like coming out of many startups as well as universities as well. And I'll also just add that like the 2024 Turing Award was won by Sutton and Barto, who are like two of the pioneers of RL. They wrote the book that most people would have read if you work on RL. And so this is like sort of, and I guess I'll try to end on this note that there's a lot of nice research going on in RL and in a diversity of different domains. And so if this is something you're interested in, now would be a good time to start working on these kinds of problems. And so, yeah, on that note, let me say thank you. And these are some, like avenues for research and some different interesting domains. But I've also added some references that, you can check out if you have the time. And if there's any questions, feel free to ask now or email me after that.
Okay, well, thank you so much, Nived. Thanks for giving the talk. Any questions? Okay, thank you. So we are already a little bit over time. So thanks, Nived, again for giving the talk. And let me just remind you, now we enter kind of the last phase of this course. So the next two lectures, we'll have project presentations, and then of course there will be a project submission. We've already sent out information about presentations as well as what is expected from the final project report. And let me just also kind of remind you that we want to be a little bit mindful of the time for each presentation. So please make sure that you stick to the allotted time when we start the presentations on Wednesday, sorry, this Wednesday. Okay, thank you so much. Okay, bye.
Yeah, thanks for the invite as well.
Thanks, Nived.